Hello, everyone, and welcome to our first event of this kind. We're excited to celebrate innovations in building products and technologies through presentations and conversations with leaders in this space. Today, we're very excited to welcome three amazing guests: Kyoung, who is the founder of EcoClosure, Chris Maurer, who is the principal and founder of Redhouse, and Shawn Torbert, who is the director of sales and business development at Hempitecture. My name is Alexandra Shkevi, and I work in design technology at a global architecture practice and also serve as a strategic advisor for Acelab. I'll be moderating today's event alongside Bo Latoza, who has a background working in architecture and is now a product specialist at Acelab. And I'll pass it off to you now, Bo, to give a quick overview of Acelab, the sponsor behind this event.
Cool. Thanks, Alex. Hi, everyone. I'm Bo. So a little background about me: I studied architecture at Tulane in New Orleans, and then I moved to New York, where I worked at OMA and a few other firms in the Northeast before I moved to Denver, Colorado, where I currently live. And I began working with Acelab as a product specialist. So I'm going to go ahead and give a few slides about what Acelab's about. And if you're interested in learning more, you can reach back out to us after this session. So Acelab is a platform that is simplifying how architects, builders, and specifiers can collaborate with building product experts and manufacturers. So our technology is data-driven, it's non-sponsored, and free to use. We are started by a team of architects. So this is some of our team who are all working to build the tools that we wanted to see ourselves in practice. And our site has a range of resources, including free AIA-accredited building science courses by Christine Williamson, who's an amazing educator. We also have construction detail, CAD and BIM libraries, all with easily downloadable files that are clean and gone through by our team. We also have search tools that make sense for specifiers, so you're able to find products that have distribution to your location and the types of ratings that you need. And then you can also compare those products easily based on cost and data so that you're able to better plan for your budget. And then you can download this information to easily communicate it with your team and with your clients. So we also have a project-based product research platform. So all of your product research you can save in one place based on your projects, so you can always pick up where you left off and not lose your research or your specifications. Okay, so with that, I'm just going to put a quick poll up. If you are interested in learning a bit more about Acelab and getting a free 15-minute demo of our platform, we're welcoming anyone on this call to reach back out to us and have a 15-minute demo. So you can go ahead and answer yes to this poll if you're interested. I'll send you an email after this event, and we can set up a call and talk about how to integrate Acelab's tools into your workflow. All right, so I'll just leave that up for a few more moments. If anybody doesn't get to answer, I'll put it back up at the end of our event. So don't worry if you don't get to it right now. Okay. And then with that, Alex, you can go ahead and introduce our first speaker.
All right. So Dr. Kim, I want to introduce Kyoung. Dr. Kim is a practicing architect, engineer, and entrepreneur. She's a professor of the School of Architecture and the director of the Integrated Design Research Lab at UNC Charlotte. Dr. Kim is joining us today to talk about her work as the founder of EcoClosure, a clean tech university spinoff that focuses on regenerable building enclosures. Dr. Kim recently won a major grant from the National Science Foundation that will fund the next stage of development of EcoClosure's high-performing window system that reduces building energy consumption and carbon dioxide emissions. This is Kim's third NSF grant in support of her decade-long research into incorporating screens of microalgae into biochromic windows. On a personal note, I was lucky enough to have Dr. Kim as a professor at UNC Charlotte. She's not only an incredible professor, but she's a really great person as well, and we're thrilled to have you today, Dr. Kim.
Okay, I'll stop sharing so you can go ahead now.
Thank you, Alex, for the nice introduction, and also thank you, Acelab, for inviting me and sharing what I am doing. So now I'm going to share my screen.
I'm reading the dictionary.
I'm sorry. Okay. Can you see all my slides? Yes.
Yep, I can see.
So yes, I am very passionate about how the building technology can, not only reduce the environmental impact from the built environment, but also impact people. So I will try to, capture both aspects that this biochromic window can, offer. So we are in the era that we call Anthropocene. So, viewed as the period during which human activity has been the dominant influence on climate and the environment. And as you know that the built environment play an important role in reducing the impacts and also, the safeguard, the safety of the ecosystems and also the human built environment. And if we keep, our business as usual, we will need 2.5 of the Earth. And then the issue is that the Earth will outlast us, human will extinct, like in the past. So we need to dramatically reduce the carbon emissions by 2030, such that we can meet the carbon neutrality by 2050. And another note I like to make is that the buildings composed of 2 parts of the carbon or energy. One is for operating the buildings, but the other one for making the materials and the building themselves. So if you look at this graph, the pink, often we ignore or overlook, is called the embodied carbon. And as population grows, then embodied carbon will increase because we need to, expand more urbanizations and we need to build more buildings. And then we oftentimes are focusing on reducing the operation energy, but we have to think about how to also offset the embodied carbons that are, emitted by these construction activities. So I have been working on these 3 design strategies to meet not only, sustainability, but also offset the carbon caused by the built environment. One is that we have to put building technology or building design in a way that it reduces the energy consumptions. And also on top of that, the renewable energy resources should be used to offset energy consumptions from the operation and also manufacturing and constructions. And finally, we have to think about how we actively remove carbon. So in my experience, again, my education and practicing as a practicing architect, we often only focus on energy efficiency of the building and also incorporating the BIPV system as an example. But we have to think about how actively reduce the carbon emissions. So this is the kind of version 1 of the biochromic windows. So design goal is that you have to balance the needs for a human, which in this case about energy efficiency and view out, and also create the environment for the microalgae to grow. The growth rate is super important because that equates to the carbon reductions and also indoor air quality improvement. So these are the earlier installations of this version 1 of our the R&D work. And then again, going back to the design strategy of the energy efficiency and renewable energy resource as well as carbon uptake, we try to minimize the energy consumption through regulating the solar gain by alternating or manipulating the density of the microalgae. And also we want to somehow find ways to reclaim the stored energy within the system for space heating and domestic hot water. end product of the microalgae out of these systems can turn into venues that can benefit the societal needs, such as human feeds, aquatic feeds, animal feeds, fertilizers, biofuels, and also as well as the soil amendment. So this is the like a very quick overview of the way we approach the biochromic window R&D. So starting from the design concept, we figure out ways to make cost-effective and scalable manufacturing the techniques, and then alongside with the design, we also carry out the analysis, in this case, structural analysis and computational fluid dynamic analysis to make sure that it is structurally sound and also provide the environment for microalgae growth. We also working with the biologists and also engineers to make this work successful. So this is the modular system of the bioreactor that can turn into different shapes and size. Closer view. So the intake of the air coming from the bottom, like a fish tank, and then the oxygen which will be produced through the top of the systems. Young algae will be filled from the top, and then the grown algae will be harvested through the gravity systems to harvest. So the system has been installed in the scrub architecture, and depending on the lighting conditions and also the different strains, we can create different light quality and the different spatiality that can impact the students' perception. Another thing that we've been working on is to actively offset the carbon dioxide. And then at the moment, ESA produced 5 gigatons of the carbon dioxide. And we did the calculations how many the coverage is required by our system to offset the entire annual carbon reductions. And we need 100 parking lots of the super stores to offset the carbon emissions. Currently, we are working on the EVA charging station that can be installed on those open parking lot space, and then we are integrating with the photovoltaic systems that can complement the solar spectrum. So, for example, green and purple in this solar spectrum are used by the microalgae, and the blue dots are utilized by the amorphous photovoltaic systems you can see here. So we are currently in the process of installing them in the school again to do the proof of concept. And hopefully we can have some initial data that can justify our hypothesis. I'd like to introduce a recent book that I published, Design and Engineering Principles for the Microalgae Building Enclosures. I have been also practicing as a building facade consultant at Front Inc. In New York City for a decade. So I am very passionate about how building services can play a role on those environmental and social responsibilities. And there are many building examples around the world that are either actualized or available as a speculative projects. And this is just a very like a short excerpt from my book, which is about the interventions at the infrastructure level and urban level and building and products. So, for example, infrastructure, we could use them as a food farm to feed human, and also we can turn the building surfaces to offset the carbon dioxide. For example, we can also integrate as a parking canopy or bus shelter as a urban technical techniques. The building surfaces play an important role for integrating microalgae systems because algae rely on the solar spectrum to grow. So these are the primary locations, and we are also looking into products, how we can these microalgae permanently such that it does not turn into carbon dioxide if we don't treat them not a proper way, they decay and then turn into carbon dioxide. So these are my presentation. And if we have questions, you can reach out to me at this contact info. Thank you.
Awesome, thank you. All right, gonna quickly share my screen again to show a slide about our next guest. And then Alex, do you want to go ahead and introduce Shawn?
Sure, yeah. Shawn Torbert, he is the Director of Sales and Business Development at Hempitecture, a company that specializes in hemp building materials with a mission to create healthy, energy-efficient habitats that positively impact inhabitants as well as the environment through sequestration of carbon dioxide. Shawn is joining us today to share more about Hempitecture and their US grown and manufactured bat insulation from hemp wool. We're really excited to have Shawn today. Thank you so much for being here.
Yeah, thank you to Acelab for hosting this wonderful event. And thanks to Dr. Kim, that was very inspiring. I studied molecular and cell biology in my undergrad work, so it's fantastic to see the intersection of biology and the built environment. So let me see if I can share my screen here.
One quick thing to add, if there are any questions, we will have time at the end for a Q&A as well. So if you have questions for any of the speakers, we'll leave about 10 minutes for audience questions.
Okay, I'm having some issues sharing my screen here.
Okay.
I think my Google may have me locked down in the privacy settings. Are you able to share? Thank you, Bo.
No problem. And then I'll just try to keep on pace with your slides, but just feel free to let me know if you need me to
Will do. I appreciate you running it.
No problem. All right, here we go. All right.
Okay. Fantastic. Thanks so much, Bo. So Hempitecture is a new company. We're only about 4 years old. We're based out of Idaho. I'm based at the northern part of the Jersey Shore near Sandy Hook and Asbury Park and sort of in the shadow of New York City. So, you know, I've been involved with the passive house community and really the focus on reducing carbon emissions, both from an operational standpoint over the last 15 years or so, and now really focusing on reducing embodied carbon in the built environment. Next slide, please. So as Dr. Kim so wonderfully teed up, as far as carbon emissions, we're going to cover some of how that impacts insulation and what we're doing here at Hempitecture. Next slide, please. So, as Ed Mazria laid out for Architecture 2030, we're really in a tough spot here when it comes to meeting the Paris Accord and reducing carbon emissions. It's well known that about 40% of the entire built environment, 40% of emissions come from the built environment in the United States. However, in cities, that can be as high as 70 to 75% of emissions coming from the building sector. And that's based on trying to reduce carbon emissions from an operational standpoint. Over the life of a building, operational energy and carbon emissions have a large impact. However, in the short term, over the next decade or two, as Dr. Kim said, and as highlighted by Ed Mazria from Architecture 2030, really have an oversized impact. So for new construction, reducing embodied carbon embodied carbon in building materials is really essential if we're going to meet the climate reduction goals, greenhouse gas reduction goals. So Hempitecture is the first company in the United States since the legalization of industrial hemp in 2018 to actually be using North American grown hemp fiber as an insulation material. So up to this point, we've been importing from our partners in Canada, but we did just complete manufacturing of our first factory in Twin Falls, Idaho. The benefit of building with locally grown bio-based fibers and manufacturing that locally is it creates, local jobs, both in the building sector and manufacturing, but also agriculture jobs as a cash crop. It shortens supply chains. As we all know, during COVID, supply chain issues for building materials was a nightmare. So we'll be able to do all of this locally. And in addition, hemp, just by its nature, it's a weed. So it, cleans the soil. It's regenerative to the soil. So if you're growing industrial crops like corn or soy, you can add hemp into that crop rotation for a few seasons. It doesn't require any pesticides or very little pesticides. It also uses less water. Next slide. So as I mentioned, Hempitecture develops, manufactures, and distributes the most sustainable insulation on the planet, hemp wool. 4 years ago, when we incorporated in the state of Delaware, we decided to do it as a public benefit corporation. So we're not a certified B Corp, but we are incorporated as a public benefit corporation. And according to Cornell Law School, a public benefit corporation is a corporation created to generate social and public good and to operate in a responsible and sustainable manner. Next slide, please. So we first started off about 7 years ago as an idea, trying to realize hempcrete building systems in the United States. And hempcrete is sort of like a natural building technique that's used widely in Europe, where you add, a cement type product to hemp fibers. And then, you kind of like a rammed earth system. And then that's finished with like old world Italian lime plaster. However, in the United States, as all of you probably know, we don't really build that way. So now our main focus is on hemp bat insulation, which is, one-to-one replacement for traditional bat insulations. Next slide. So why hemp? As I mentioned, it's a weed, so there's high yield per acre. It doesn't require fertilizers and lower water use than other types of crops. It's inexpensive and abundant. It regenerates the soil, and in addition, we can use the entire plant for different products. So the flower will go to like CBD production. The seeds go for hemp oil and health foods. And then we actually use the stalk to create the fibers. And estimates are that an acre of hemp can offset or sequesters approximately 10 tons of CO2. So each acre of hemp is the equivalent of taking 2 automobiles off the road. Next slide. Oh, and I forgot to mention it, because it is a weed, it can basically grow anywhere in the United States. So again, our primary product is hemp wool insulation. It's a one-to-one replacement for traditional insulation products like fiberglass bat or mineral wool insulation. We own the trademark and IP, which, as I said, we've been importing from Canada to already supply projects in the US for the last 4 years. And we just finished completion of construction of our factory in Idaho. Next slide. And we'll be testing our first runs of American grown and American manufactured hemp any day, which we're very excited about. As a material, there's no VOCs, no toxins. It's non-allergenic. It's safe to touch, so you're not going to get the itch like you get, or the fibers like fiberglass, if anybody's ever worked with, or mineral wool, which is very abrasive. And it has better performance just from its dimensional stability, and it's the way it's friction fit into the interior stud cavities or partition walls for acoustical insulation. Next slide. Looking at the embodied carbon of insulation, there's hemp fiber down on the bottom there. It has a negative embodied carbon footprint, and you can see how that compares to other types of insulation materials. Next slide. And here's looking at an 13 bat, which is like a traditional 2x4 type of assembly or thickness of insulation. And the key thing to look at here is, as driven by the energy codes, or if you're going for net zero energy ready or living building challenge or passive house, these insulation thicknesses are going to be, 10, 12, sometimes even 15 inches thick. So the positive numbers there that you see, like for mineral wool, for example, 608, you can imagine if that was, a 6-inch stud, that would be a third higher than that. If you're going even thicker, that would move to the right and have a larger embodied carbon footprint, while, the materials, the bio-based materials that sequester carbon will move to the left and have a larger impact in reducing that embodied carbon impact. And this is important because I'm not sure if everybody knows, but New York City just had an executive order requiring embodied carbon analysis for all city-owned buildings, really focusing on the concrete and steel industry, which are, heavy industry polluters for manufacturing those products. And then, also a full building life cycle analysis. So where projects are requiring now to account for and reduce embodied carbon using bio-based materials like hemp wool can help offset the heavy industry materials required for large scale construction like we have in the cities. Next slide. Sizes are standard sizes. So 2-inch, 3.5-inch, 5.5-inch, 7.5-inch for wood frame construction, either 16-inch widths or 24-inch widths if you're doing advanced framing techniques, and they all come in 4-foot lengths. Next slide. And we'll see if this video works. If not, installing hemp wool insulation is very easy. Essentially, it's friction fit. So basically, you take the hemp wool out of the bag and you stuff it in and kind of pat it into place, making sure that it fills the cavity completely. It's not overly compressed. And then the adjacent panel above it, starting at the bottom, working up, you friction fit it into place so it butt joins, or it's butt jointed against the panel or bat below it, making sure there's no gaps, and you have a nice monolithic continuous insulation in that stud cavity. Next slide. So here are some fresh pictures that have, just from last week of our first facility in Idaho. As I mentioned, we're very, very excited about this. It's been a lot of work, and we're, thanks to the support of all of our funders. We were crowdfunded to get to this point. We've grown organically and really bootstrapped ourselves to this point. And the goal is to, get our first test runs going here in the next coming weeks. And then once we fine tune that and our recipe based on the hemp grown in Montana and the genetics of the hemp fibers grown here in the United States, which we are currently working with Oak Ridge National Laboratories to dial that in for the US market. We'll be able to repeat this in any community that grows hemp, industrial hemp in the United States. Next slide. So here's a video that's probably not going to play, but this was from our prototype manufacturing. Essentially, it's, the fibers are layered and it goes through a compression. We add about 10% of textile polyester as the binder, like you have in pretty much, all your clothes. And then we get these kites cut and then bagged. Next slide. And thank you.
Thanks,
You're
Shawn.
on mute, Bo.
There we go. Thank you. Thank you, Shawn. That was awesome. I know a few people entered some questions during your talk, so we'll get to those at the end. And I'm going to quickly introduce our next guest. Okay. So our next guest is Christopher Maurer. So Christopher Maurer is the founder of Redhouse Studio. He's an architect, an innovator, and a researcher. Redhouse Studio is based in Cleveland, Ohio. They are currently working to develop building materials and processes from biomass waste that can create food, save water, and sequester carbon. They're also working with NASA researchers to develop self-growing off-planet structures that will save transport costs by using in situ resources and building biomass materials at destination. And Chris is going to be joining us today to share about his work using biomaterials, which are materials that use the growth of organisms in their manufacturing in limited resource environments. All right, Chris, I'm going to stop sharing my screen and you can go ahead and try. Let me know if you have any issues. There you go. Okay, and I think you're just on mute still, Chris.
Can you see my slides? Are we starting with Redhouse?
Yep, you can see your slide.
Okay.
There you
Great. So from weed to mushrooms, this is perfect.
go.
I really enjoyed the presentations. Thank you, Bo, for the introduction. As you mentioned, I'm Chris Maurer. I'm from a studio called Redhouse in Cleveland, Ohio. And we do a lot with Micro-texture, and that's why I mentioned mushrooms. That's actually building using fungal mycelium, which are, a lot of people consider those the roots of mushrooms. It's actually the vegetative form of the fungal organism that creates mushrooms, but a good way to think about it is mushroom roots. We have three major projects that use fungal mycelium, what we're calling Micro-texture. One you mentioned, the second one there, the work that we're doing with NASA to actually produce buildings off planet that we're actually using algae as the substrate for growing the fungi on. So I will be ordering Dr. Kim's book and looking really closely at that, different ways to do that. We're experimenting with fungal bioreactors that become parts of walls as well. And then that algae then becomes the substrate for growing mycelium and creating strong composite materials that can do all kinds of things, include protect from radiation, ionizing radiation that is consistent outside of the Earth's magnetosphere. The third one you see there is our biocycler, where we're actually looking at taking construction and demolition waste and using fungi to not only recycle that into new materials, but remediate it as well. And so there's a lot of toxins in the built environment, a lot of petrochemicals, polycyclic aromatic hydrocarbons, sometimes referred to bitumen, asphalt, those kind of things. But there's also a lot of elemental toxins too, including heavy metals like lead. And so we have a few different ways of attacking the toxins that are in the environment and either breaking them down into smaller molecule chains or doing the opposite, which is chelating and taking those elemental toxins and turning them into longer molecule chains that are then not biologically poisonous. They're inert biologically. But the one I'm going to talk about mostly today is the first one there, MycoHab, where we say we're providing food, jobs, shelter, and access to high-tech equipment. And I'll kind of I'll unpack that a little bit. But this is a project that is in Namibia, which is the south western part of Africa. And what you see there in the background of the video is fungal mycelium growing. So the reason why we're looking at that as a potential building source is because it grows so quickly. Yes, hemp grows really quickly, but mycelium is another organism that you can grow tons of material in days if you have the right infrastructure for doing that. Not only that, we can provide food and other things in the same process. So I want to first start with some numbers. This crowd seems to know probably a lot about this, but the embodied carbon footprint is a huge aspect that we need to tackle. And if we want to get to carbon neutral by 2050, there are 200 billion tons of building materials made every year. 3 of those materials, concrete, steel, and aluminum, equate to about 23% of the carbon emissions from those materials. And a lot of that, most of that, in fact, 84% of that is just in raw extraction of the material. So this is mining things, processing, turning them into new materials. And so this is where the circular economy, or using circular resources, recycling and renewing materials, can be super advantageous, because we can decrease that whole raw extraction part of that. There are about 230 billion square meters of buildings that will be built by 2060. So I mean, imagine every building in the world and then double that. And that's how many buildings we're going to make by 2060, 2.5 trillion square feet. So, you know, one of the big things I want to translate here are buildings are big. That's a very important takeaway. There are 3 places I think we can store carbon efficiently. Oceans are our biggest resource. We can store carbon there. The ground, second biggest resource, land. And then our third one, the ones that the humans actually build, are buildings and infrastructure. So that's our third biggest opportunity to actually take carbon from the atmosphere and store it somewhere. So buildings are big. So how can we do that? So we can use plant-based materials, because plants actually draw down carbon through their life cycle. And if you're able to keep them from re-emitting that into the atmosphere, either by burning or digesting, or by just letting decay, say in landfills and things like that, then that carbon will be locked away. Whereas normally part of the carbon cycle is recycling that back into the atmosphere. That's normally a good thing if we weren't emitting so much carbon. That would contribute to a healthy carbon cycle. But another way to do this is to take that carbon, store it somewhere. And as I mentioned, buildings are a great place to do that. The way you kind of calculate how much storage you can do in a given plant-based materials, to take the organic carbon, and then you multiply that by 3.67. So this is carbon dioxide molecules, which are really big. They get converted into carbon, you know, atoms that are in different molecules. And then the carbon dioxide equivalent of that is 3.67. So you see there in the slide in the background, wood is obviously a good choice for taking carbon that's been drawn down from the atmosphere and then putting that into buildings. But again, this is something that requires a somewhat renewable resource. I would argue not very renewable resource. So to look at wood as our savior here would require massive deforestation. And so again, we want to look towards circular economy. Things like agricultural waste. So this is stuff that's already going to waste. After farming different grains, there's straw that's left over, and the straw is used for bedding and different things in construction to protect mud from going into the street. But if we were to actually use straw in buildings, in the case of like straw bale construction, we could, if we use all the straw, we could offset all of the transportation emissions in the United States. That's kind of a 1-for-1 exchange. So imagine the impact we could have by taking some of these waste materials and putting them into buildings. That brings us to Micro-algae. So this is a project that we're working on in Africa. There's different locations where we've started this, but our main one is in Windhoek, Namibia, where we're turning Namibia's encroacher bush into food and building materials. This is Namibia. On the left there is the traditional state of affairs, where you have grasslands, but on the right is what has become of much of Namibia, where the encroacher bush, or the blackthorn bush, has taken over large swaths of land. And this is based on the way that when colonists came, they cordoned land and set up fences and changed animal migration, and we have this bush that's now leading to desertification. So the Ministry of Agriculture wants to get rid of a good percentage of it, not all of it, because some of it is good for evapotranspiration and things like that. But they figure that there's at least 330 million tons of material that can be sustainably harvested every 15 years and can go to value-added goods. Most of the time, this is going to fuel pellets and charcoal and things that are burned, which re-emits that into the environment. We call that carbon neutral because it, you know, at least it's offsetting petrochemicals, fossil fuels, and it's drawing down that carbon, then releasing it, whereas fossil fuels are basically just releasing them. But there may be a better way. You could turn this into, again, building materials and even food, in the example of what we're doing here. So this kind of shows the process in a nutshell. So we take that encroacher bush, we grind it up into sawdust or to powder. Then we plant them in these large vertical columns with a little bit of mycelium. The mycelium grows through there, inoculates the entire column, and then mushrooms start to grow out the sides where we have these holes drilled. It's really easy just to take a spackle knife and harvest those mushrooms. We turn those into value-added goods, things like medicinal compounds or jerky, or even fresh mushrooms that go straight to market. Those could potentially expand into an export culture for Namibia. And then the waste material that's left over, the thing that's in that column, can be pressed and turned into a building material. And so this is how we get this equation. The 1 kilogram of this waste material can turn into 1 kilogram of mushrooms and 1 kilogram of building materials. And not only that, we have 1.5 kilograms of carbon storage. All of those things could be used as income generation for our partners in Namibia. I work with a physicist at MIT, and I assure you there's no laws of conservation being violated here. We are adding water, we are adding air, we are adding all kinds of free resources to this equation that makes it all kind of play out physically. But basically the takeaway is 1 kilogram of waste material turns into all these beneficial things. This is our humble facility in Windhoek, Namibia, where we're growing the mushrooms in the shipping containers and actually pressing them in these small outpost type designs. We're looking at packaging this as something that's deployable to other locations, something we call micro-hab in a box, where we can kind of ship this to different locations and enable small scale farmers to set up a farming facility as well as a building material manufacturing facility. Here the process is, again, kind of showing this up close, where the custom grow columns allow for easy harvesting of the mushrooms as well as the mycelium byproduct, and then that's pressed and baked into a structural material from cultivated waste. Here is one of it's a very unscientific test, but one of the funnest tests that we've done about the strength of the material compared to a concrete block. It's much better at resisting impact, as you see there. But a lot of these other tests were done in laboratories at MIT and Stanford. So you can trust them a little bit more than the sledgehammer test, that the mass pound per pound or kilogram for kilogram, we have the same here, but we can get compression strengths that are twice as good as in materials we make here in Cleveland. The bending strength is much better. The insulation value is much better. And then obviously you compare carbon and food production and all of those things that concrete doesn't even stand a chance. So the biohab construction works like this. We have different formworks. We've experimented with inflatable formworks, and this kind of came from our work with NASA, that we could have inflatables reused over and over. We're now using more traditional formwork. It's a little bit safer to use, but we build arches, move the formwork, build another arch, and then you could theoretically have a building that's miles long when you continue to add arch to arch. But then it's covered up with a metal roof that then is either recyclable or reusable, and then the building material that's protected underneath that, the micromaterial is at the end of the day compostable if you were to remove this protective layer. Here are some of the photographs from on site. We continue to test the material and test the assemblies that we're making. We build them up, wreck them down, and basically, try and see what they can take. But we're in the process of building our first prototype that we're actually going to leave up and have there. We call this boundless growth. The reason being because when your byproducts are things like food and housing and ecology, then you can see how kind of proliferating this would have a positive effect, whereas most materials are carbon emitters. Micro-hab uses circular resources and regenerative biofabrication to provide food security, bolster water security, regenerate wildlife ecologies, provide low-cost shelter, and store carbon. And so a lot of times we say these mushrooms are building homes, and we're very clear to say we aren't building homes of mushrooms. The mushrooms are harvested, they go to market, people eat them. I would never build anything out of food itself, because food should be food. But for every pound of mushroom we sell, that equates to 1 pound of building materials that go for humanitarian housing in Africa. With just 1% of the encroacher bush, we could do as many as 16,000 microhabs. With 10% of the encroacher bush, we could do as many as 165,000 microhabs, and that would be enough to house the 500,000 or nearly 1/4 of the population in Namibia that are housing insecure, that are currently living in shacks, that could be living in formal settlements through this process. It's a partnership with Standard Bank, which is Africa's largest bank, MIT Center for Bits and Atoms, and my company redhouse. We've now started a company called Microhab, based in Mauritius and working throughout the world. And last slide, I'll just leave you with my email address if anyone would like to talk further about this. I'd love to hear from you. Thanks.
All right, awesome. Thank you so much, Chris. Thank you to everyone. That was a really wonderful discussion. It's really cool to see how you all have worked that's, different but related. So with that, I know we've had a few questions already posted in the Q&A. Some questions for Hempitecture. Can you see these on your end, Shawn, or would you like me to read them aloud? There's a few questions about.
I got the Q&A open, so
Cool.
just start at the top.
Yeah, you can start with any of those you'd like to answer. Also, if any of the panelists have questions for each other, I know, that could be interesting to kind of hear about, what your presentation sparked for each other. So, feel free to ask each other something as well.
Great. Okay, so the first question looks like it's from Marisol Foreman. Is hemp wool fire resistant? So in its natural form, and the one that we've been importing from Canada for the last 4 years is Class C fire rated. The US produced version, we just had tested at Intertech. We add a bio-based flame retardant to it. So, no borates, no chemicals, it's bio-based, and that we got Class A fire rating from Intertech. So as we start US production, it is Class A fire rated. Next question which is Hempitecture 2 from Danielle Culbertson. Does re-wetting degrade the performance of the hemp bat over time? So in general, when insulation gets wet, it loses its R value. What's interesting about, for example, like fiberglass, very traditionally used as a bad insulation. When that gets wet, it loses like 100% of its R value. So it's basically totally ineffective. Hemp wool, on the other hand, the hemp fibers have the ability to absorb about 20% of its weight in water and not degrade R value. That being said, it's also vapor permeable. So you really want to make sure the entire assembly has drying potential to either the interior or exterior, or both, depending on your climate zone.
And then I'm just going to skip down. I see a few more questions have come in. So there's one for Dr. Kim here. Can you describe your ideas to transition from research to practical market-based products a bit?
My idea, I think I am trying to take advantage of being educator. So students will outlast me, and while they are in school, nurture the ideas with me, and also working as a research assistant on the project. And then hopefully they can, make a little bit of ripples and then the bigger waves later on. In the practical side, I'm also actively seeking the finance sponsorship mainly from the federal grants, federal agency, and also professional organizations. And then I've been also, I think those are lucky to have people around me who share the same vision to change the society. I know this is very abstract, but again, being educator was a good position. Yeah.
Great. Okay. And then there is another one that is for kind of all of the panelists. What are the chances of making any of these into very large scale operations? So if anyone wants to comment on that, maybe Chris, that could pertain to you.
Yeah. I think good for, and I'll speak for everyone, I think good chances for all of them, because it's going to be completely necessary. You know, as I mentioned, we're going to double square footage of buildings by 2060. If we build with concrete, if we build with, you know, steel, other methods that we're building with right now, we're only going to exacerbate the climate issues that are going on right now. So there needs to be these either carbon storing or carbon sequestering materials in the future. We're looking at scaling up. So we have one plant in Namibia now. In 2023, we're already looking at doing this in Austin, Texas, Mauritius, and a few European locations as well.
And just real quick with Hempitecture, we're already scaling up. As I mentioned, our first factory just completed construction. That took us about a year. So we should be able to scale quickly in any region of the United States that grows industrial hemp. And we're looking forward to do that, especially up here in the Northeast.
Great.
And Chris, I think there was one for you as well that somebody was asking, do you see this platform being implemented for all kinds of agricultural efforts? Meaning, could and should a vineyard use this and build their winery and Ecolab with similar technologies and incorporate the local foods initiative?
Absolutely. And so I could see almost any farming practice is going to have agricultural waste. And usually that agricultural waste would be good fodder for growing mushrooms. So, you know, if you want to vertically integrate all of these things, that you could turn not only the agricultural waste into something for another agricultural process, then the agricultural process waste becomes, you know, what the building material can be made out of. So I think, yeah, absolutely, there are ways to tie this to different farming techniques. And, you know, I'll just mention that mushroom farming is the least consumptive of water out of any kind of agricultural practice. It uses about 10% what you need to grow vegetables, and about 1% of what you need to grow meat. So, you know, I'll just, you know, say, you know, per pound protein, this is the best way to actually kind of create food security as well, using the least amount of water.
Great. I see another question just came in. I think this is for Shawn, but something I'm wondering about too is the water shortage in the Southwest. Will the water shortage in the Southwest open more market for hemp?
I mean, not necessarily. You know, all crops need water to grow. So even though hemp uses less water than some of the other industrial crops, you know, I mean, if you don't have water, you can't grow anything, right?
Right. And
There's one about hemp. Again, can the hemp be recycled, not downcycled? And are you working on or plan to work on using an alternative to the polyester additive?
Yes, good question. So currently, no, the end of life would be, you know, landfill or, you know, into waste to energy types of disposal. But for right now, unfortunately, no. But we are working on a bio-based solution to the polyester, or perhaps even a recycled PE or PET binder in, you know, but yeah, you're right. If it's, you know, has the plastic in there, that's problematic for end of life, but we'll find a solution.
Just real quick for anyone who missed the intro in the beginning about Acelab, if you would like to sign up for a free 15-minute demo, I'm going to relaunch this poll now so that you can answer to let us know, and we'll follow up with you after our event. We can keep going with Q&A. I also wanted to answer a few questions I've seen about after the event, if we can access slides. I also know our speakers all shared their contacts. So yes, we'll be sending follow-up emails after the event. If you'd like PDFs of the slides, you can feel free to request them. We'll also be sharing a recording of today's event. Yes, so a recording will be available. And we'll also be sending out a survey, just asking kind of what we would like to hear about in the future. So if you can fill that out, that's helpful as well. Okay, great. This question for Hempitecture looks like it mostly got rated, fire rating performance, how's the crop farmed, and it looks like you're answering another. So if that's all our questions for right now, I want to thank all of our speakers again once more. That was really a wonderful discussion and really informative. So thank everyone for taking the time.
Yeah, thank you all.
Thank you, everyone. Thanks, Acelab.
Thank
All right.
you.
Thank you. And thank you to all our guests who joined us today. All right. Have a great day, everyone.